Okay, I'm ready to start the calibration on here. I've got some gear warming up. What do we got going on? We've got the TM5006 frame, which has all the calibration plugins. I've got the frequency counter warming up just in case I need it. We got the 6500, the 7603s warming up, and the Rigol is also warming up just in case we need it. Get the calibrated binder under here. Just get that tucked in so you guys will be able to see it. I actually, doing the calibration, I like putting a binder under here because it lets me look square on to the graticule and lets me get everything lined up a little bit better. So I'm gonna let the scope warm up. I turned this on about 2 minutes ago. So it needs a half hour to an hour to warm up. And then I will be able to dive in to doing some adjustments. Okay, I'm set up to measure the first step, which is the 59.4 volt rail. For the power supply checks, it specifically says, let me use my pointer, to use the ground on the power supply board. So that's where we're at. 59.4 is over here. And I really can't ask for better. I'll show you. Well, 59.4 volts. Okay, now for the plus 50 volt. Well, I can't ask for much better than that. I've got a tolerance of 0.05, so 50 millivolts. I'm within 10, so actually 9. So perfect. Okay, the calibration routine wants us to buzz through the rest of the power supply board real quick. So I apologize for the ping pong, but I'm going to show the test point and then I'll move over to the meter. Plus 5 is here. Tolerance of 100 millivolts. Perfect. Plus 15 is right next door. Tolerance of 0.25. Looks good to me. Minus 5 is right here. Looks good. Tolerance is 100 millivolts, so we're at, yeah. It's perfect. It should also be noted that all of this is ground reference to the ground point on the power supply board. So the low side has not needed to move for any of these. Next one's negative 15, tolerance of 300 millivolts. Negative 15 is one back. Man, there's a lot of supplies in this scope. Okay, negative 15. My tolerance is 0.3, so that's fine. Next up is 5.5. Negative 5.5 is right next to the ground reference point. Tolerance is 0.25. Perfect. Plus 5.5. Well, I couldn't ask for better than that. Next up is negative 9. Okay, here's negative 9. Negative 9 is fine. Plus 9 is fine. Here's plus 9. Here's the setup for plus 25. Plus 25 is fine. Test point for plus 120 volts, and I'm allowed plus minus 2.4. Perfect. And here's the setup for the 180 volt test point. And tolerance on this is plus minus 3.6. So couldn't ask for better. Okay, for step 4, they want me to remove a transistor and check the calibrator amplitude because I have a high enough frequency scope. I'm just going to check it right on the scope. So I'm going to use the Rigol to check this. So let me and it wants 5 volts off the calibrator signal. 5 volts peak to peak. So we are good there. Speed it up, just check it at a megahertz too. Yeah, so the calibrator's fine. Okay, so the calibration routine wants us to do a bunch of stuff with a scope and a few other things to do set the frequency of the calibrator. I have a frequency counter with enough digits, and it's backed up by a rubidium standard, so we're just going to calibrate directly to the frequency counter. It is off. This is the potentiometer I'm going to be adjusting, and I will move you guys up to the frequency counter. Okay, so we want to adjust this for as close to 1 kilohertz as possible, and I need to speed this up so I can actually see it adjust, because I just really shot it into outer space. Oh, not too bad. Was I moving the wrong resistor? No, but I had it set wrong. Gotta let it lock back in. Gate, time, enter, gate, no, time. 1 second for better accuracy. Not super accuracy, but good enough for this adjustment. Speed it up again. All right. Well, that's about as good as I'm going to get the 1 kilohertz. I had to play with it for a little bit. So 1 megahertz is next. Can't ask for better on the 1 megahertz. So there we go. All right, we're set up for the cathode regulator test point. And we're looking for 95 volts plus or minus 8 volts. I'd say we're within spec. Okay, time to check the spicy voltages. We have the appropriate high voltage probe, and it should be known that I already have the ground clip hooked up. So we are going to measure the negative 3000 volts. And it's plus minus 500 volts, so 2% accuracy. So oh no, sorry. So 2950 to 3050 is what I need, and we'll touch the point. Like so. A little bit of corrosion. All right. So it's not possible for me to move the camera, but I am at 2,978 volts, so that is fine. I had to rotate the tip of the probe to clean it up. Either clean some tarnish off the tip of the probe or clean some tarnish off the joint so I can get a good measurement. Because even with 3,000 volts, I was still having a high impedance connection and it wasn't going to the meter correctly. But high voltage is good. The CRT neck pins for step 9 are down here. Extreme caution is needed against this red wire. That's got the full acceleration voltage of the anode on it. My measurements are 45.9 and 46.6. Okay, my calculated average is 46.25. I need to hook the meter up to... I'm going to put the shield back on, and then I got to hook the meter up over here. Okay, so 1796, the PL comp resistor is right here. And my calculated average was 46.25. I'm reading 46.50. And I'm allowed 300 millivolts difference. So it's very close. I'm going to adjust it a little bit, see if I can't true that up just a bit. However, it is actually within spec. Well, can't argue with that. Okay, so I'm ready to do the grid bias, which if you've never done a scope before or are just using these videos to get one up and running, for the health of the tube, grid bias is probably the most important adjustment for the life of the tube. If it's wrong, it overdrives the tube, and it'll age it a lot quicker. If it's too low, it's not going to have the brightness it needs, and you're going to struggle to get the speed out of it. So very critical adjustment. Take some time. Get this one correct for sure. I have it set up. That's the Z out on the DC. With everything completely off, it was at 8.28 volts, which is where it's expected. I increased it to 12.3. And now I need to adjust the grid control, which is actually on the bottom right now, so I have to turn the scope 90 degrees. So you can see the spot right here, well defined. Everything is good. We want it just on the threshold of visibility. I can still see it barely. Just on the threshold of visibility in low light. And I'm going to go a little more. All right, I can barely see the spot. The camera can't even pick it up. It's there, only because I know where to look, because I can't pick it out. Actually, I can't pick it out on the screen, but it's there. So that's the grid bias. All right, we've got a test probe hooked up to the high-frequency output of the Z out. We need to look for how good the square wave is. And we also need to look for rise time. So I'm going to get the Rigol set up, get it triggering, and then we'll take a look. You'll want to position this off the tube because it's really bright, so I zip it off down the side to take a look. Let us take a look at what we've got. All right, so here's what we got. Let's see if we can clean this up a little bit. Yeah, it looks all right. Don't have a lot of ringing. But our rise time's a little light. We're on a 20 nanosecond rise time, so we need a little bit. We need to pull some capacitance out of this, make it a little bit quicker. So C17 6265, and R1765. Okay, here's our three Z-axis compensation adjustments. There's a potentiometer hiding down here that you can't see because of the two capacitors, but it's these two caps and then that resistor. I'm going to fiddle with them, and we'll see if we can't clean up that waveform a little bit and speed the rise time up. Okay, after playing around with the controls a little bit, we have a nice sharper corner, and we're at a 14 nanosecond rise time, so we are within specification. Okay, checking the Z-axis modulation, I have a 200 millivolt signal going into the front end of the scope at 20 megahertz, and we do see Z-axis modulation. External trigger as requested. I also need to check now, let's see, 0.5 microseconds, and we need to go to 2 volts peak to peak and 2 megahertz. I'm using my RF signal generator because it'll do it. This is pushing the output a lot, but amplitude 1 volt, frequency 2 megahertz. And we also have amplitude modulation, and wow, that is bright. I'm not going to let that go for too long. The reason I did the generator at 1 volt is due to it's designed for a 50 ohm input, and it outputs 2 volts into high impedance, which is what we were at. Okay, here's all the gear hooked up. The probe is on the autofocus, or the DC test point. We have autofocus being monitored. We have autofocus being monitored by the DMM. And I need to take note of what the autofocus gain is, which is 162.77 volts. Now I need to increase this to a 50 volt step. This is on the test oscilloscope. All right. And that went down to 140.23. So I'm going to turn this down so I can find my test point. I don't want this burning too long because it's pretty bright on the tube. Okay, autofocus gain is way over here. And what we're looking for on the tube is best focus. Well, that one didn't improve too much. Okay, the way this works is you have autofocus gain, and Z max, and you kind of bounce back and forth between these two, and then you set this with the intensity all the way up to a 72 volt step on the test oscilloscope, and that is how that one is done. Check out waveforms with sweeps running at 1 millisecond of division. So step 14 is just checking the outputs of the back of the scope, making sure they're working. And then 15 is trace rotation. Okay, just checking our external signals. Gating, A gate's working. We have to get it to fire B sweep. The B sweep is working. So I have A gating and B gating. And then we should have a sweep. Yep. We have an A sweep sawtooth. So that is all our external sources is working. We know focus and a stig is working. And we should be good, so we're up to trace rotation. To be perfectly honest, looking at that, trace rotation is good, so I'm not even going to mess with it. Trace rotation's on the back corner where the outputs are, but in this case, it is good. All right, got to get some time markers in. Okay, so the calibration routine says it wants 1 millisecond and 0.1 millisecond markers of full screen amplitude on channel 1. Well, I'm going to do this with the TG503, which can't do double time markers at a time. So we're going to do this with 0.1 time markers. To get the double time markers, you have to have a 184. It doesn't work on the TG501. So we're going to do this a different way because I've got everything lined up as it is right now. Actually, I need to bump this up a bit and bring this down. Give me some more intensity. So there we go. We have full line time markers. So we're going to bump this to 0.1. We're going to bump this down to 0.2, which will give me 2 time markers per division. And what I actually want to do, so my settings for this are 0.2 on the time base, 0.1 on the time mark generator. And this one's actually looking pretty good. But what I want is a full time marker on this graticule and a full time marker on this graticule. And if I needed to, I would use the variable time division to adjust that. And because the time markers tilt, they're not straight on the way down, I actually need to line up a little bit. So what I want to do is I actually want to come down and I want to use just the tips. That's actually perfect right there, a perfect setting. So you want to use just the tips to line this up. So if I get this tip right there, so having the delay sweep out, I have this tip right here and I have this tip right here. Now the important part is this tip is lined up with the center graticule line. If this tip isn't lined up, then you want to adjust the y-axis, which is R1794. So this is a way you can do this adjustment if you don't have a 184 and you can't do the double time markers. This is looking totally okay, no problems. This is very nicely lined up, so I don't need to mess with that one. And actually, while we're at it, I'm going to go pop down one more. Roll that off screen. I'd say geometry looks pretty good. Yeah. I think I am going to adjust the geometry just a little bit. It's grid bias, geometry. Here we are. Oh yeah, that's very bowing. That's pretty bad too. So you can see at the extreme edge of the control, we have a lot of bow down towards the bottom. So if I bring this up, We have lots of curved lines. Need to straighten that out. I'm going to move the camera real quick so I can be straight on, and then I'll bring everybody back when I get this adjusted. Well, I'd say that's going to be about as good as I can get that. All right, we need to adjust the horizontal gain. Punch that in. Horizontal display to B time. I'm on B time. Okay, this concludes the calibration or the alignment on the power supply and the tube. The next video will cover the horizontal section, and then we'll see what else is next in the calibration alignment process. Thanks for everybody for joining me in the lab, and I will see everyone in the comments and in the next video.